Hello and welcome to my presentation for the ECE 528 final project called StormDroid. So the problem I wanted to tackle has to do with outdoor excursions. With more than 168.1 million Americans participating in outdoor activities each year, places like national parks, ski resorts, and other popular outdoor points of destination really don't have any cell service in a lot of places. So I was inspired to tackle this problem when I was hiking with a bunch of friends. We were above tree line and we saw some dangerous clouds roll in very fast. And we weren't too sure whether to stay up above tree line or climb back down. But ultimately, we decided we didn't want to be struck by lightning. So we went down. But I wanted to make this app to help people with that decision and potentially give them better data. Um, and this can encompass, hiking, rock climbing, many different activities while being a completely offline application. The goal of the application was to create a deep and reliable model, 100 megabytes or less in size, while having a low inference time for live inference and low battery usage. So with this, that code has to be both the cloud type classification model and pressure data modules within the application, along with all the UI and other Kotlin components. So the user can make quick decisions just on one UI regarding potential dangers. One of the bigger challenges in creating the model was finding clean data from an on-the-ground point of view for cloud type classification. A lot of the cloud data sets out there are from satellite images, which do not help when you're trying to classify clouds from the ground. TrailSense is an outdoor companion app that contains a linear regression based cloud detector, along with other utilities like star map, uh, cooking times for different foods, hiking trail maps. But the model for the cloud classification is pretty weak, and I wanted to improve upon that with a deeper model. There are other related works like on Kaggle, there's some cloud classification contests, but none of those are deployed to an embedded environment. After settling on the problem that I wanted to tackle, the next step was gathering and augmenting data. So after sifting through Kaggle, the Cloud Photo dataset was perfect as it pre-split 474 images into training and 486 images into validation. And these two sets were split into 7 categories. So I used the image data generator function from the TensorFlow image preprocessing library to cleanly turn those and augment the images into inputs for the model. And those values were 224 by 224 input shape, a batch size of 32, and I normalized the pixel values. So with that data input size, I was able to use the ResNet 152 v2 model as a base layer for transfer learning. I unfroze the last 14 layers and fine-tuned the model, and then a global average pooling 2D dropout and 7 neuron dense layer were appended onto the final fine-tuned model. And then finally, I used dynamic range quantization to convert the final model into a TF-Lite file. For the Android code approach, I split it up into 4 modules. The tensor class first is utilized to initialize and load the model during application runtime. Then I use the Camera X Android Jetpack library for capturing bitmap input. The camera is also displayed on the UI, so you can see what you're sending to the model, and that prediction refreshes every 5 seconds. And along with this, the pressure module is the statistics below the cloud type that you can see on the right, and it spawns a background processes that periodically capture this data. So it's not just the data that you're using while you're on the app, but also when the app is running in the background. And then the main UI simply ties this all together to provide you a live feed of the classification along with these statistics. So the results met the goal that I was aiming for with the final model and code being 77 megabytes. The battery usage was only 313 milliamps for a total of 15 hours on the 4700 milliamp battery, and I achieved 90.7 model accuracy after compression with a 98.8 millisecond average inference time. Though some categories perform better than others, the final result, along with the previous slide's data, shows a nice diagonal line having 91% accuracy in the test on the confusion matrix. Overall, I successfully deployed a very deep model onto the Android device while keeping battery consumption and inference time at a minimum, and users can reliably use this to identify potentially dangerous conditions while completely off the grid. But the limitations for my project is that the dataset did not include images at night, which makes this application only usable during daylight. I could have tested on more devices as I only use the Google Pixel 9, and a more custom model could possibly achieve the same accuracy while being smaller in size with further compression techniques.